This next chapter on quantitative analysis in budgeting then is basically providing us with the numbers to put into our budgets. So we have to be able to forecast in the future what we think we're going to be spending on labour, materials and other overhead costs. And what we're doing here then is learning the nuts and bolts of the tools to give us those calculations and give us those numbers for inclusion in our budget. The first area that we'll be looking at then is the HighLow method. So we'll be looking at remembering, because this is assumed knowledge, how to calculate an expected level of fixed cost and an expected level of variable costs so that we can use the total cost function y equals a plus bx to predict what the costs will be for a given level of activity. Something new then that we'll be looking at, and the bulk of the emphasis in this chapter, is to do with learning curves. So what we'll be looking at is basically saying the more you do something, the better you get at it. So as cumulative output doubles, then the average time taken to produce those units falls by a given rate. So we're saying then you're going to get a bit quicker, and we can try and quantify the amount that you're going to get quicker the more you do something. There's a formula then which we'll be looking at in the chapter y equals ax to the power b. Don't worry about remembering that though, because you get given it on your formula sheet, and we'll be looking at what to do with it. As well as looking at the calculations, we'll also be thinking about some of the conditions for a learning curve to be able to be used, and some of the problems. These will make a good focus of a discussion question for a few marks to pick up some straightforward marks. Learning curves then, this improvement, are going to cease at some point, so we'll be looking at what happens and the calculations involved in reaching that steady state and what we can use the numbers for once we've found that out. Finally then, we'll be thinking about how we can apply this to things other than time. So we might get more efficient at using materials, and we might also be more effective in overheads if we're taking less time to produce something. So anything other than labour then that's reducing because of our experience is known as the experience effect.
In order to prepare a budget, you're going to have to be able to produce forecasts of costs and revenues. And what we're going to do is to look at various different techniques for how these forecasts can be prepared. Some of them will be familiar to you, so we're going to start with the HighLow method. Absolutely crucial method, because you'll need to be able to do this in various different types of questions. Not just in budgeting, but it could also be used in variance analysis later, where you look at what your standard costs are, splitting between the fixed and the variable cost. So this example is designed to just give you a bit of a reminder as to how to do it. We've got 3 levels of production in terms of units, with 3 levels of labour. So the important point here is that labour is a semi-variable cost. So inside, for example, that 27,000, some of it will be fixed and some of it will be variable. And the whole point of the HighLow method is to split them out between the two. So we just do a step-by-step approach. It's called the HighLow method because you take the highest and the lowest output levels. So in this case 14,000 and 10,000, and you look at what those labour costs are at each of those levels. Find the difference between the two, and that then gives you the variable cost per unit. So if your output goes up by 4,000, the costs go up by 8,000. Therefore, variable cost per unit has got to be 8 divided by 4, or 2. You then substitute that variable cost into the total costs, remembering of course that total costs are equal to the variable costs plus the fixed costs. So if you like thinking in terms of algebra, you could do it that way, or you can just use the common sense approach and how we have shown it here. So our total costs are 35,000. If the costs are 35,000, the variable cost there, you've made 14,000 units, and it's at $2 per unit. So your variable cost must be 28,000. The difference between the two gives you your fixed cost. Another useful little bit of prior knowledge to remember is the total cost function. So what we do here is we have the equation of a straight line, which we're going to use also when we do regression analysis later in this chapter. The idea is that the y is the total cost, a is the fixed cost, the intercept on the y-axis, b is the gradient, and that's your variable cost, and x is the number of units that you produce. And the whole idea of this is that you can actually draw it as a straight line. So looking at our diagram here, we've got y on our vertical axis, that's the total cost, and then the output, in other words the number of units, is x, which is on that horizontal axis. Where it crosses the y-axis is the intercept, so that's a, and that's fixed cost. So what that means is that even if you don't produce anything, you still incur those costs. And then the slope of the line, the total cost line, is the variable cost. So for every unit extra that you produce, it will go up by the variable cost. Now obviously what that assumes is that fixed costs stay the same and that variable costs per unit are constant. But what could happen is a volume-based discount. In other words, you get some sort of discount for buying in bulk, and that will alter what this looks like.
So learning curve theory is based on the assumption that the more we do something, the quicker we get at doing it. Now that means that our labour costs and potentially our variable overheads, if they're driven by labour hours, will fall later in production. Now this is something we tend to use for new products, because obviously once we've been producing a while, we've already got as efficient as we can be. Now let's have a look at some of the conditions that need to exist in order for the learning curve to apply. Our production needs to have a significant manual element to it. If it's just an automated production, the machines aren't going to get any quicker. So it needs to have a manual element. And that element needs to be repetitive, so that the more we do it, the more we can learn and improve, get quicker. As we've mentioned already, we need to be an early stage of production if we're going to be able to improve. And in terms of the workforce themselves, well, there needs to be a consistent workforce. If we've got different people coming in and out, they're not going to be retaining the learning. No breaks in production. What that means is no significant breaks, no sort of long periods away from this, doing something else instead. And we talk about having a motivated workforce. Now, what we mean by that is that the people that are working, as they start to learn, they can get quicker, they will get quicker. They're not just going to plod on at the same rate as before. Now, our learning curve theory says that as our cumulative output doubles, the cumulative average time per unit falls. Okay. Now, the key thing here is we're looking at this doubling. Output doubles and then this learning curve percentage applies. So it's not with every extra unit that we make. Now, to show this on a graph, you can see here says the cumulative average time per unit. It falls as we make more and more units. But we do get to a point where this flattens out, and this is known as the steady state. That's where we've got as quick as we can at that, and actually this is now the amount of time it's going to take us to make our units. We have a look at example 1. We have a workforce here that has a 75% learning rate. We're told that the budgeted time for the first batch is 100 hours, and we've got to calculate the time to produce 8 batches. Now you can see here, to make 8 batches, we've got this doubling of production. To start with, we make 1, double that is 2, double it is 4, double it 8. Now we know that when we make that first batch, it took us 100 hours. So our average time for that batch was 100. Now when our output doubles, we make 2 batches, the cumulative average time falls to 75% of what it was. So that means that would take us an average of 75 when we made 2. Now remember, that is just an average, so to find the total time, we would need to multiply that by 2 to give us 150 hours. When our output doubles again, falls to 75% of our time. So at 4 batches, we're looking at 56.25. Now again, to get the total time, we'd need to multiply that by 4, which would give us 225 hours. So lastly, when we make 8, the cumulative average time, 42.19 hours. If we want to know the total time to make 8, we multiply that by 8, and we have 337.5 hours. So that's the time that we're interested in here. Now that's all very well when our output is doubling, but what if it isn't doubling? Well, when that's the case, we have to use a formulae. So I've got it here, y is equal to ax to the power of b. So a is the time for the first unit, x is our number of units, and b is this index of learning. Now we calculate that by saying log r is your learning rate, so in our last example log 0.75, divided by log 2. Now that gives us y, and y is the cumulative average time to make X amount of units. So let's have a look at using our formulae in example 2. Same set of data as before, a 75% learning rate, and the first batch is 100 hours. But this time we've got to calculate the time for the first 10 and then the time for the 10th batch. The first thing it's worth doing is finding your value for b. So log 0.75 over log 2 gives us minus 0.415. Okay, now you should always have a minus here because our time is reducing. So if you haven't, you've done something wrong there when you put that into your calculator. So let's drop that into our formulae. So y is equal to a, the time for the first unit, which was 100 hours. We want to know how long it takes to make 10 units. So x is 10 and we've just calculated b. Now the answer this gives us is that cumulative average time per unit. Okay, so that is not the time for all 10 batches. It's the average time when we make 10 batches. So we have to take that 38.459 hours and multiply it by 10 to get our total time. Now B was asking us for the time for the 10th batch only. Now again, this isn't the 38.459 because remember that is just the average. It's not the actual time for the 10th batch. So what we need to do is say, okay, how long does it take me to make 10 batches? How long does it take me to make 9? One from the other will give me the time for the 10th. So we know the time for 10, so in order now to work out the time for 9, basically we're just going to drop 9 into our formulae here in place of the 10. Now remember again, this is giving you a number of hours per unit. So multiply that by 9 to get our total hours. We can then take those two total times, one from the other, gives us 22.99 hours for that 10th batch.
Here we've got a slightly different situation then, because Flowgel has already prepared the first batch of the product and it took 200 hours. We're told there's a learning curve effect of 85% and we want to know how long it's going to take to produce the next 16 batches. It's very important then when we're looking at the next 16 batches that we remember that they've already benefited from the learning effect of batch number 1. So batch 1 will have generated some learning. So what we're looking for is how long it takes to make batches 2 to 16. And so what we're going to need to do then is we're going to need to calculate the total time to produce the 16 batches and then subtract the 200 hours that have already been spent on the first batch. So this is the sort of thing then to look out for, especially in section A questions. So using the formula then, y equals ax to the power b. Well, we've got then a learning rate of 85%. So that will be equal to log 0.85 divided by log 2. So the rate of learning will be minus 0.2345. The first batch then took 200 hours, so A is equal to 200 hours, and the important bit here is to remember that X is going to be equal to 16. So 200 multiplied by 16 to the power minus 0.2345 will give us the cumulative average time for the 16 batches. That's 104.4. Multiply that by 16 and that will give us the total time for those batches. So the total time for 16, but we need to deduct from that the time for the first batch. So that will be 1,470 hours. Using the same information as before, what we need to do is work out for Flowgel what the time will be for the steady state. So we want to work out then what the steady state, once the learning has ceased, what the steady state time will be. So what we're going to need to do here then is we're going to need to work out the time for the 30th batch. You don't want all of the time for the 30th batch, you want the time for just the 30th batch, because we'll use that going forwards as the time for the standard cost card in the steady state. So the approach then is going to be to calculate the total time for 30 batches, and we're going to subtract from that the total time for 29 batches, and that will give you the time for just the 30th batch. So once you've worked out what you need to do to work out the time for the steady state, you just need to do the calculations in the same way as before. So the total time for 30 batches, I'm going to use the formula y equals ax to the power b. We know that b is equal to minus 0.2345. That's log 0.85 divided by log 2. We know that the first one took 200 hours, and x here will be equal to 30. So this is a good opportunity to make sure that you can pop this into your calculator, and you may wish to do the calculation, pause the recording and then do the calculation to check that you're happy popping it into your calculator. So the cumulative average time for 30 batches is 90.08, and if we multiply that by 30, that will give us the total time, which is 2,702.5 hours. Then we need to do exactly the same with 29 batches, but this time x is going to be 29. That'll be 90.8 680, multiply that by 29, and that gives you 2,633.3 hours. Take the difference between those two, 2,702.5 minus 2,633.3, and that will give you the difference, which is 69 hours. And for the steady state onwards, 69 hours per batch will be budgeted in the standard cost card once that steady state has been achieved.
Now, section 3 deals with the experience effect. The experience effect is exactly the same principle as the learning curve. It's just that we only use the term learning curve when we're talking about labour. Those same benefits that we get that we can apply to other areas of the cost card, we refer to as the experience curve. So for example, the more units we make, we can probably access some better deals with suppliers or some bulk purchases, and therefore obtain some discounts, so the cost of our materials might fall per unit the more units we make. So exactly the same principle. Any other item though is an experience curve rather than a learning curve.
Okay, so at the end of this chapter then is a good time to have a look at question 3 from the pilot paper, BFG. It's also time then to reflect on what we've studied in the chapter. So the HighLow method then, which is an approximation then of what element is fixed and what element is variable cost, using the difference between the total costs at the highest level of output and the total costs at the lowest level of output, and saying that if we assume fixed costs are constant, all of the increasing there must be due to variable costs. We represent all of this then, these fixed costs and variable costs, through the total cost function, the straight line y equals a plus bx. So the total costs then are equal to the fixed cost plus the variable cost times by the number of units being produced. The main focus of the chapter then was about learning curves, so saying the more you do something, the better that you get at it, providing certain conditions are met, i.e. it's a new product in a repetitive production with a significant manual element. We also need, remember, to have consistency in our workforce and no breaks. And the rule is then that as cumulative output doubles, the cumulative average time per unit falls to a given percentage. So the percentage rate of learning then will be how much quicker we were than we were previously. And we can calculate this easiest using the given formula y equals ax to the power b. Whilst we get better and better, they'll reach a point where you can't get any better, perhaps because the workforce have got a go-slow agreement or their physical limitations have been reached, and that's what we call the steady state. Final thing then is that the experience effect is when learning curve theory is applied to anything other than labour. The calculations then are quite tricky initially with the learning curves, so it's worth working back through the lecture examples and questions, because once you work out how to do these and make sure you're happy with them, they're quite methodical if tested in the exam.